So, one-way valves are important for many applications, from rockets to plumbing to hydroelectric power to much more, and even new designs for jet engines and stuff. But there's a couple problems with one-way valves. One of them is all of them impede flow to some extent, so flow doesn't move smoothly as if there was no valve there. How fast they respond, some one-way valves turn off the water in one direction a lot faster, or turn back on a lot faster or slower. Electronic controls could do a lot better, but the problem with electronic controls is they require sensors and stuff that might malfunction, and it adds complexity and stuff like that to it, and power usage. And also one-way valves also experience significant wear and tear. Now, let's first go over the typical one-way valves. One of them is a ball valve, which is very simple. There's a little container with a hole in the one end. Now there's other ways of doing it without a ball, but there's a little hole at one end, and when there's water flows, it pushes the ball or something to the hole and clogs up the hole. When water comes in the other way, that little ball goes the other way, unclogs the hole, and there's a bigger end at the other end, so it can't fully so water can flow past the ball when it goes in the opposite direction. Another way is to have like a V-shaped valve. And this V-shaped valve, when water flows in one way, it spreads out the V. So when it flows into the V, kind of, and that blocks out the water. If it flows in the opposite way, it closes it. It instead flattens out the V, so V collapses and water can flow more easily. The advantages of the V run is that it can more quickly respond and everything, but it's in theory. But you have to find a flexible material, which is harder at high flow rates and high temperatures and low temperatures, or with really strong chemicals. It's much more likely to break. There's a lot more wear and tear because it's open and closing a lot. The ball valves can be made for many more conditions and a lot stronger and a lot more reliable, even though slower to respond. They're also easier to manufacture. Another one is a Tesla valve, which is a lot more complicated, but I have some pictures of a Tesla valve. Tesla valves do not respond nearly as fast as other valves, theoretically, but they respond more consistently. So if you rapidly change the flow back and forth, a Tesla valve might work better because it's not vibrating or shaking, which I'll get to more later on actually. But beyond that, they also have they have no moving parts to wear and tear, but they do take up much more space and will make your plumbing bigger. And they work in that one way it flows more smoothly than another way. Tesla valves can also be made of much more durable materials because of just the design feature, but they also can give more of impedance in some cases. Now, one way we could get rid of some of these problems with a ball valve is to make it respond a lot faster and a lot better would be if we made nano ball valves or micro ball valves or many small ones in these arrays, because the ball doesn't have to travel as much. It could respond a lot faster. Each ball would also experience less force. The problem with making any of these valves, though, too small is vibrations. When it hits this thing, or when it changes direction, or if there's any vibrations, it might start shaking it, and it might not always be in this little hole perfectly blocking it up. Same as this small one, and vortices could be generated, and everything else. You can see that with like small stuff, it's just not as stable. And then if this whole thing is vibrating, that can lead to more wear and tear. All bad things. Tesla valve will have actually less of this problem. But I've come up with a solution for fast responding that I think will have less wear and tear also. And here is my solution. So, first of all, we'll have this black thing would be a mess, but it's a solid mess. Here, with very small gap, but lets the water through or whatever, Here we have a mess. And this mess, when water goes one way, I should do that a different color. But anyways, if when it goes one way, it pushes it out and expands a lot more. This secondary mass that I draw in a different color and really lets in fluids past it. And it can be folded in, but when it goes in the opposite direction, it folds in on itself. Like origami, it can recompress. So it acts like a bunch of small valves all tightly packed together because of the mesh-like structure. Like how a cloth can suddenly expand much more when you blow in air, and the little gaps can become suddenly big ones, or it can collapse to a fuzzy thing together. And by figuring out a specific geometry, you can make it very strong and very porous or not very porous, which is a small change of how much expand or not. And to stop it from going the other direction, you have this mess here, which I do in black partially, but you can also have the structure collapse on itself and become more solid, more in one direction. And all this could lead to a very fast response. And meshes, because there's so many support material and so interwoven like a fabric more, it can be amazingly strong. Fabrics themselves can be amazingly strong compared to other things, so you can handle up high pressures, and you can make these fabric meshes out of metals because people have, and plastics and even ceramics, some materials that normally could not make it, meaning you could handle a lot more high temperatures or a lot more harsh chemicals. Well, thank you very much for listening. Please like and subscribe. It really helps the channel out. I'm trying to reach 1,000 subscribers in a year and 4,000 watch hours, which is really hard. With your help, I think can do it. Also, if any ideas for future videos, comments, or suggestions, please leave them in the comment section below. Thank you very much again. Goodbye.